Hi, ladies and gentlemen. Sorry for the meeting this morning. I went through this whole thing and then went back and lost you all. So we're going to go ahead and get started with the LeChatelier's principle of class practice. The first thing that it wants us to do here is rewrite the reaction, include energy. So if we look at our delta H value here, it's 85 kilojoules. It is a positive value when energy is positive. That means energy is being absorbed into the reaction, and it is endothermic and a reactant. The next thing we're going to look at is the number of gas particles. You always want to look at your states of matter. Everything here is a gas, so we're going to count everything. I have 1 plus 1 gas particle there for a total of 2. And then I have 2 on the right because I have a coefficient of 2 there. So I have 2 gas particles for reactants and then 2 for products. Okay. First thing we see here is adding hydrogen. When you increase either concentration or temperature, the reaction is going to shift in the opposite direction. So if I increase hydrogen here, the reaction is going to go into the opposite direction. It's going to shift to the right. When we add a catalyst speeds up both the forward and the reverse reactions. So they go both directions. And the reaction then does not shift at all. It just speeds up both reactions. So this is going to be a no change. Removing iodine. So if I remove iodine, what's going to happen is it's going to pull the reaction back to the same side. It wants to make up for that and make more iodine. So the reaction is going to stay on the left. So when you remove something, whether it be energy or concentration, it always pulls it to the same side. So the reaction is going to stay on the left there. If I decrease temperature, that is the same as removing energy. So if I remove energy, again, the reaction is going to pull and stay on the same side. It's going to stay on the left. Number of gas particles is where I look at for pressure. Since my gas particles are the same, increasing or decreasing pressure are not going to have an effect on the overall reaction. So this is going to be no change. And if this is no change, this is also no change. All right, so adding hydrogen for the next one. The reaction shifted to the right. Our change in hydrogen concentration. Whenever you see this, I always tell students to write down whether it's a reactant or a product. H2 is a reactant. Reactants are on the left-hand side. Since they are on the left-hand side of the reaction, when the reaction shifts left, then your reactant concentration will increase. So anytime you see left, it's going to be increase. And when it shifts to the right, it's shifting away from the reactants, so the reactant concentration will decrease then. All right, going down now to letter B here. It says rewrite the reaction to include energy. So we're going to start off by including energy there. Negative 132 kilojoules. Since the value is negative, that means the reaction is exothermic and energy is a product. It is being released or given off in the reaction. The next thing we're going to look at is the number of gas particles. You always start by looking at the state of matter. Our reactant is a solid, so I have 0 gas particles on the reactant side. On our product side, sodium ion and hydroxide ion are both aqueous. So I have no gas particles on the product side either. That would also be 0. Now going and looking at the stresses. Sodium hydroxide is the first stressor that we are doing, and that is a solid. As you recall from the notes, solids and liquids have constant concentration. They do not have variable concentration. Because of that, they will cause no shifts in equilibrium. So when you add a solid or a liquid, it's always going to be no change, no change. An increase in volume Boyle's law states that pressure and volume are inversely proportional to one another. So if I'm increasing volume, it's the same as decreasing pressure. It's always good to just deal with one idea instead of two. So I always change everything that says volume into pressure. Pressure depends on gas particles. Again, since my gas particles are the same, they are both zero, that is not going to have an effect on equilibrium. That's going to be a no change, no change. Decrease in the concentration of hydroxide. So we go and we look. Hydroxide's aqueous, so it will have an effect on equilibrium. If I decrease hydroxide, it's going to pull the reaction to stay on the same side. So that is going to be on the right side of the reaction. And an increase in temperature. If I increase temperature, it's the same as increasing energy. That's going to cause the reaction to shift to the opposite side. It's going to shift to the left then. Now here we're looking at hydroxide concentration. Hydroxide is a product. Products are on the right-hand side. Therefore, when I shift to the right, that means my product concentration will increase. And if I go to the left, products are not on the left. It's moving away from those, so the product concentration would decrease. Okay, letter C here. The number of gas particles is where we're starting at again. So we want to look at our states of matter. Everything is a gas here, so we're going to count everything. On my reactant side, I have a coefficient of 1 and 3, so a total of 4 gas particles. On my product side, I have a coefficient of 2, therefore I have 2 gas particles on my product side. Erase that. So the first thing we're looking at here is an increase in pressure. An increase in pressure is going to favor the side with fewer gas particles. I have fewer gas particles on the product side, which is on the right. An increase in volume is the same as decreasing pressure. A decrease in pressure is going to favor the side with more gas particles, which is on the left-hand side. So the reaction there would shift left. Decrease in ammonia. If I decrease something, it pulls it and keeps it on the same side. So the reaction would shift right. And an increase in nitrogen. If I increase the concentration of something, it's going to shift to the opposite side. So if I increase nitrogen, it's going to shift to the opposite side, which is on the right. Change in product concentration. Products are on the right-hand side. So anytime I go to the right, I'm going to increase concentration. And if I shift to the left, I'm moving away from the products, so there will be a decrease in concentration. And this is when equilibrium has been reestablished. So once equilibrium has been reestablished, you have an increase or decrease in the overall product concentration there. All right, looking at 14 now. In the above reaction, when the temperature is increased, the reaction shifts left. All right, so this is all we really need to know here. If I increase temperature, that's the same as increasing energy. And if I increase temperature or concentration, we said the reaction shifts to the opposite side. Well, it's shifting left. That means that energy must have started on the right-hand side then. I'm going to erase this, clean this up. The energy must have started on the right-hand side in order for it to shift to the left. If I increase energy, it's going to shift to the opposite side, which is the left-hand side. So energy would have been on the right. If energy is on the right, energy is being released. It is an exothermic reaction, and it's going to have a negative value of delta H.